Hello, class. So on this video, we're going to start on section 2.1. Right, so we're going to go back now to chapter 2, section 1 in the book. And I mentioned that the reason I waited until now to cover this section is because the two methods that we've covered so now, in terms of how to solve or find the general solution of a differential equation, they both work for nonlinear differential equations. Right, so we had the separable equation method where you don't have to start with the linear differential equation. And then we also have the exact differential equation method, which again, you don't have to start with the linear differential equation. So the two methods that we've seen so far work for either linear or nonlinear. So they're more general than the ones that we're going to start looking at now. Okay. All right, so starting from now on, all of the methods we're going to be looking at are going to be methods that only work for linear differential equations. Okay. The only exception, which is not actually going to be a solution method per se, but it's going to be an algorithm that we're going to be using Mathematica to compute approximations. Right, so I mentioned a long time ago that in most cases, when you're working with actual differential equations in real life, you can actually find solutions like we can in this class. You're actually going to have to approximate them. So that's the only exception to this rule. But other than that, all we're going to see is how to find solution methods for linear ODEs, whether they're first order, second order, or higher order. Okay. So this section, section 2.1, is titled, or I'm just going to call it integrating factor, right? Because the method that we're going to use to solve the linear first order differential equation is called the integrating factor method. And the method is actually kind of easy to come up with, so I'm just going to run you through it. Okay. So first of all, just let me remind you that a first order linear differential equation has this form. There's some expression involving x and constants times dy dx, some expression involving x and constants times y equals some expression involving x and constants, right? So one thing I mentioned is you can always divide by this function here in front of the derivative, right? Because we know this is not equal to 0, because if it were, this wouldn't be a first order differential equation. Right? So if you divide both sides by a1 of x, you get this differential equation. Again, it's the same thing. We're just dividing by a1 of x. Now, it's not 100% accurate that it's the same thing, because if you notice here, there is a new restriction on the variable x, on the input variable. Right? Now, that can't be equal to 0. So if we were talking about what the domain of this differential equation is, so what input and output variables, what independent and dependent variables we can plug in, we're restricting the ones we can plug in here. Okay. But in terms of finding the solutions, it's going to be easier for us to work if we write it this way, and then we can just worry about what the x values are later. And I'm gonna talk about that in a moment, anyways. Okay. So we can write it like this, and then we can just simplify this even more and just write it as dy dx plus some expression involving x and constants. So I'm just going to write a naught divided by a1. It's just p of x equals g of x. Right? So I wrote h divided by a1 as just g of x. Okay. So this is going to be our general form for a first order linear ODE. This is where you want to keep in mind anytime I mention those words. Okay. Now, what's the solution method? Well, the solution method is going to be this. Can we find a function, let's call it mu, just the Greek letter mu. So can we find a function mu of x such that we can multiply it to both sides of the ODE, by mu. Right, so I'm going to multiply both sides of this differential equation by mu. So let me do it in a different color. Right, so dy dx plus p of x y equals mu of x times g. Right. So I'm trying to find a function mu such that I can multiply both sides. So you can multiply this differential equation on both sides by anything, but I want this mu to be special. Right. What's a special property that I want mu to have after I've multiplied everything by it? So such that the left-hand side becomes mu of x times y prime. Okay. Okay, so this is the setup. We have a first order linear differential equation. Our goal is to find a function mu such that when I multiply both sides of the differential equation by mu, the left-hand side, right, so all this becomes just the derivative of this function mu times y. Yeah. That's the goal. Now, why do we want that? Well, if the left-hand side is just a derivative of mu times y, well, we can integrate with respect to x, because this derivative is with respect to x. So actually, let me write it more clear here before. So I'm going to start using that shortcut. But for now, let me write it as, to make it clear that the derivative is with respect to x. Right, so these are both functions of x. So it could have been clear before, but I just want to make it 100% clear. If the left-hand side of this ODE is this derivative, if we integrate both sides with respect to x, well, the derivative is going to go away. And then we can just divide both sides by mu, and we get our y. Right, so that's the idea. Now, of course, how do we find such function mu that satisfies this? Is it even possible that such a function mu even exists? Well, let's see. Let's figure it out. So again, we're trying to find a function mu such that this left-hand side becomes this derivative. Okay, so what do we have here? So dx, so let's first see what this derivative is. We know we can use the product rule. We learned that in Calc 1. So by the product rule, this is mu of x times y prime. And again, I'm going to use the prime symbol because it's clear what variable we're taking the derivative with respect with, plus mu prime y. Again, we want this derivative to be equal to the left-hand side of the differential equation. What's the left-hand side? Well, it's mu of x dy dx. Right, so I'm just rewriting this here. Mu of x dy dx plus mu of x p of x times y. So we're trying to find a function mu that makes this true. Now let's take a look at these two things. In order for these two things to be equal, what has to happen? Well, the first term is already equal to this term, so that's fine. Now, the only other thing we need for these two things to be equal is we need whatever's in front of the y on this side to be equal to whatever's in front of the y on this side. If that is true, right? So the first terms are already equal. If that is true, the second terms are equal. So then this equation, this is actually an equality. So what it means is, for this to be equal to this, what we need, let me do it in a different color. What we need is, we need mu prime of x to be equal to mu of x times p of x. So we need for this to be true. Now, this is actually a differential equation that we can solve. Why? Because it's separable, right? We have a derivative equal to some expression not involving the dependent variable, and the dependent variable. Remember, in this case, the dependent variable is mu, right? So it's a separable differential equation. How can you solve a separable differential equation? Well, we know the process. Just divide both sides by the dependent variable and integrate. Right? So I'm going to write the parentheses x. It's clear. It should be clear from now that mu is a function of x. So I'm just going to drop it. So we have mu prime equals mu times p. It's also clear that p is a function of x. I'm going to divide. So it's separable. Right? This would be our expression involving the dependent variable. This would be our expression involving the independent variable. So as we know, we just divide both sides by the dependent variable and integrate. So we get mu prime divided by mu equals p. Integrate both sides with respect to the independent variable, right, dx. Okay. So again, this is all just things we've seen, right? So I'm just going to go a little bit fast, do the work. We know that the left-hand side, once we do the substitution, mu prime times dx is the same as d mu. We know that the left-hand side becomes d mu over mu equals integral p dx. Now, we can't actually find what this right-hand side is, right? Why can't we do that? Because we don't know what p is. So let's just keep focusing on the left-hand side. We know here that an antiderivative for this is the natural log of the absolute value of mu, right, plus a constant, equals integral of p dx. Move the constant to the other side. Okay. Now we want to get rid of the natural log, so we take the exponential of both sides. Oh, yeah, I don't need to write the function of x. Now we can get rid of the absolute value, writing plus or minus. Right, so we get this equals, already wrote equals plus or minus e to the integral of p dx plus c. Again, as you know, as we've seen in previous videos, we can rewrite this more simpler just by taking so let me rewrite it as plus or minus e to the integral of p dx. Using properties of exponentials, we can write it like this. Then as we saw in previous videos, we can write this even simpler by taking all of this. Right? This is an arbitrary constant, so we can just write it as an arbitrary constant c times e to the p dx. Right? So now we have an expression for mu. Mu equals a constant times the integral times e to the integral of p dx. Right? And now, not only this, we can simplify this more. Why? Well, we're only looking for one function mu. This is giving you infinitely many functions because of the c. We only need one. But remember what the goal was. Find the function mu such that when we multiply the differential equation on both sides by mu, the left-hand side becomes this derivative here. Remember, that was our goal. Okay. So we only need one mu. So in particular, we can just choose c to be the most simplest constant to work with. We can let c be equal to 1. If we do that, then we get our final expression for mu. And now we've constructed the function mu that if we multiply it on both sides of the differential equation by mu, the left-hand side becomes this derivative. So again, I'm just going to rephrase that, just write it in terms of the differential equation that we had. So this is a mu such that after we multiply the differential equation on both sides by mu, this is what we did. And actually, let me get rid of the x's again, because again, it's clear from now that this is these are all functions of x, right? And again, by construction, this mu satisfies that the left-hand side of this differential equation becomes the derivative with respect to x. So again, it's with respect to x. That should be clear now, so I'm just going to write it like that. Now, why is this good? Well, just integrate both sides with respect to x. Right? If we integrate both sides with respect to x, well, the derivative cancels out, right? Mu times y is an antiderivative for the derivative of mu times y, by definition. So this side becomes mu y plus a constant equals the integral of mu times g dx. And then we can solve for y, right? Subtract c from both sides. And then divide both sides by mu. And you solve for y. So that's why it's useful for us to write it in this form as a derivative. Now, everything here we can find because we know what g is. Right, g is whatever is on the right-hand side of the differential equation. Mu is the function which we just found. Mu we can find as long as we can integrate p. P we know what it is because p is this part is what's multiplying y in the original differential equation. So everything here, there's no variable here, or there's no function here that's unknown. Everything here is explicitly defined. We know what they are explicitly as functions. So this is an explicit solution for y. Okay? And this is the method. Okay? So let's just recap. We started with a differential equation. Let me erase all these underlines so I can just underline again when I'm going through the recap. Okay. So we started here with star. I mentioned this is a general form of a first order linear differential equation. Our goal was find a function mu of x, so a function of x mu, such that when you multiply both sides by this function mu, so multiply both sides of the differential equation by mu. Oops, let me use a different color. Well, what happens when you do that? Well, the left-hand side becomes this derivative. So that was our goal. Find a function mu that satisfies that. Okay, so how do we find mu? Well, we took this and expanded it out, right? Just using the product rule. And our assumption was that we want that derivative to be equal to the left-hand side of the differential equation. Right? So this is the derivative. This is the left-hand side of the differential equation. We noticed that for these things to be true, it has to be that mu prime is equal to mu times p. And then from there, we just got a separable differential equation. We know how to solve those. We found an expression for mu, right? Now, once we find an expression for mu, then we're done. And then here, I was just telling you how that helps us, right? Making it more clear. Once we know what mu is, once we multiply both sides of the differential equation by that, the left-hand side by construction becomes this derivative. Which, once we have that, well, now it's easy to solve for y explicitly because we just integrate and then just solve as we would. Okay? And this is the method to solve for a first-order linear differential equation. And again, let me just say something. The only assumption here that we need is, well, this integral here has to work. P has to be integrable. As you learn in Calculus 1, there's a couple conditions that make P integrable. The easiest condition is, if P is continuous on an interval, it's integrable on that interval. Okay? So I'm going to formalize this as a statement in the next video, but this is basically the integrating factor method. Find the function mu, multiply both sides of the differential equation by mu, so you can go through this process and solve for y explicitly as a function of x.